Capacitance, parallel plate capacitors, energy stored in the capacitors, and the combination of capacitors. So coming to our first question today, there are the 4-point charges minus q, and these are the placed at the corners of a square. So let us go for a square first. So we are placing at the corners of a square here. So this will be the minus q, and this is minus small q, and this is going to be the 2q, and this is 2 into capital Q, so that the potential at the center has to be 0. That means potential because of the first charge and second charge plus third charge and the fourth charge, sum of all these potential has to be 0. What is the formula of the potential, by the way? V is equal to 1 by 4 pi epsilon naught charge q by distance something r. So the distance to the center from every corner is going to be the same. So this is also constant. So denominator is also constant in the potential. The only leftover is going to be the charge that's going to play the important role. So that means it will be the minus q minus small q plus 2q and plus 2 into capital Q should be equal to 0. So this will be the capital Q plus small q is equal to 0 in that sense. So potential will be 0 if capital Q is equal to minus small q. That comes out to be our first option here. Now, so four electric charges plus q are being minus q. Okay, they are being placed at the corners of an square of side length. So this total length is going to be a 2l. Okay, so this is the one information he has given. So the electric potential at this point A, which is a midway between the plus Q, and that means the distance from the plus Q to the A should be L, and the plus Q to the A should be L, and this is another distance from the corner, and this is your another distance from the corner. So two charges, both the plus Qs have same distances, same charge, same value. So I'm taking them combinedly as an V dash is equal to 2 into this is kq by distance is L. So k is nothing but n. K is equal to 1 by 4 pi epsilon naught. I'm writing this one. Next, V dash is because of the both the negative charges or V double dash, which is equal to this is 2L. This is going to be the L. So hypotenuse is going to be the root 5L. So that is 2kq by this is root 5 times of the L. So total, but these are the negative charges, so I'm going for a negative sign here. Total potential will be the V dash plus V double dash. Substitute the values here. The common things that you can take out is going to be the 2kq by L, and in the bracket 1 minus 1 by root 5. This term will be left over. Replace the k, so that will be the 2q by 4 pi epsilon naught L into 1 minus 1 by root 5. This should be your option. So this is your option C. Now, so these first two questions are of the model, that is the total potential he is asking. So this is the one of the method only finding the potential case. So these it is another model where we are going to get the relation between the electric potential and the electric field. That is the relation between them is E is equal to minus this is dV by it is going to be the dr or dl or anything dr bar, or you can write this as an electric field E bar is equal to minus of dou V by dou x partial differentiations plus this is dou V by dou y along the y-axis, that is j component here, and plus dou V by dou z along the k, that is z-axis. So this is the relation between the electric field and the potential. He has given the potential relationship and electric field at that particular point he is asking. So now if we go for the differentiation of this one, so that means your E bar is going, it's a partial differentiation, it will be the minus of, so dou V, if I substitute the V here, that means for one thing I'll do here, dou V by dou x means dou by dou x of It is 6xy minus y plus 2yz. For the x, it will be the variable. Remaining terms will be the constant. So it will be the 6y. And these two terms, since no x is there, so those terms will be 0. So like this, we need to go for it. So it will be the minus of, first term will be 6y in the I direction I cap. Second term, that is you are partially differentiating with respect to the y here. So that means your first term will be the 6x minus 1 plus 2z j cap, and the last term you're differentiating with respect to the z. So first two terms will be 0 and the last term is 2y into k cap. Substitute the corresponding values of the x and y in the given relationship. So it will be the minus of, so x and y are 1, z is equal to 0. So that means it should be the 6I cap plus, so 6 minus 1, z value is going to be 0 here. So this is going to be the 5 j cap, last term plus 2, that is k cap condition. These are your things. So where it has been here, it is in the fourth option. Okay, so this sum is also of the same model, but instead of there, he is asking the electrostatic force x. That means we need to go for another step. So electrostatic force is equal to electric field into the charge q. So first we need to find the field, and then we have to find out the force. So electric field E bar is nothing but an E bar is equal to differentiation of this one. So dou V by dou x means this will be, the first term is going to be the negative of, it is 6 minus 8y I cap. Directly I'm writing this one. Plus second term, when you differentiate the entire equation with the y, first term will be 0, second term will be minus 8x minus 8, and the last term, if you differentiate with respect to the z, first three terms will be 0, and your last term will be your 6y into k cap. So now substitute the values of the all the ones. So it will be the minus of 6 minus 8 I cap plus minus 8 minus 8 j cap plus 6 k cap. Now on solving this one, you should be getting it as a 6i. Okay, so okay, fine. This is going to be the minus 2, minus of minus will become plus 2i, and this will be the plus 16 j cap plus minus of 6k cap. So this one substitute or multiply with the charge, you will be getting the force, and for that force you just go for the magnitude. It will be the 4i cap plus 32 j cap minus, it will be the 12k cap. So for this one we have to find out the magnitude, then you can get your corresponding thing, please. So next one, the electric potential V at a point, the electric potential V at a particular point is going to be x comma y comma z all in meters in space is given by the 4x square. This is the voltage he has given. The electric field at the point 1 comma 0 comma 2 in volt per meter is. So same thing he is asking. So differentiate this one. E is equal to negative of dou v by dou x. So this will be the minus 8x. Substitute the x value, x is equal to 1. It is minus 8 volt per meter. So it should be along the negative x-axis. Fine. So next one, please. So all the three models we have covered, that is the relation between the E and the V. So now three charges plus Q, each plus Q, are placed at the corners of an isosceles triangles A, B, C. The sides A, B, C and AC. The sides BC and AC are 2A. This is also 2A and this is also 2A here. So BCE and CA are the midpoints of this one here. The work done in taking the charge from the Q from D to E. So you want to move a charge which is at the D to the E. So he is asking the work done. So potential energy at the D and potential energy or the electric potential V at the D is equal to the electric potential at the E. So that means your potential difference delta V between those 2 points VD minus VE will be equal to 0. So work done is equal to potential difference into charge. That will also be 0. So this is your next one. This one. Next one. So charges plus Q minus Q are placed at the points A and B respectively, which are at the distance 2L apart. So the distance between the A and B is going to be this is 2L. Fine. So now C is the midpoint of the AB. That means this is L. This should also be L. So it's a semicircle. This should also be L. Work done in moving a charge plus Q along the semicircle CRD. So work done W is equal to change in that is potential energy that is minus of delta U, or it can be directly initial potential energy since negative is there. So final potential energy. So initially potential energy that is Ui is equal to initial potential energy will be 0 because so 1 at this one plus q is being placed, at this one minus q is being placed, it's a midpoint. So net potential initial will be 0. That is because of the A and because of the B. It's a negative charge and it's a positive charge. So now final potential energy, if I take it to this side, now the distance from the A to the D is going to be 3L and the distance from the B to the D is going to be the L. So if we substitute that particular information, that is going to be the initially that is 1 by 4 pi epsilon naught q into this is between minus q. You are moving a charge capital Q, okay, by the distance is going to be the 3L and another one from here to here, that is minus 1 by 4 pi epsilon naught of q. So minus of into this is capital Q by distance is going to be simply L. So now when I take down the LCM and put it over here, a minus sign is also there. And then your work done will be coming out to be. So W is equal to the minus of minus is going to become as this one. So it will be the q square by or capital Q into small q, that is 4 pi epsilon naught L. If I take them common and then if I solve this one, so it comes out to be the 2 by 3 terms it will be. So this goes for 2 times and it will be the capital Q into small q by 6 pi epsilon naught L with a negative sign will be there. So this will be your condition. Next one. Two charges mark Q1, Q2 are placed at a distance of 30 centimeters apart. As shown in the figure, the third charge Q3 is moved along the arc of a circle of radius 40 centimeters from C to D. The change in the potential energy of the system is Q3 by 4 pi epsilon naught. It is also the same model sum, that is the work done or whatever initial change in potential energy. What is its initial potential energy? U initial or U1 can be written as an. This is 1 by 4 pi epsilon naught will be common in all the cases and it will be the first thing from between the Q1 and Q2, sorry, Q1 and Q3, since it is in centimeters, it is 0.4 I'm writing here, plus next one, the distance from the Q2 to Q3 will be how much? It is 30 and this is 40, so this has to be the 50 centimeters in the sense 0.5 meters, so it will be the Q2 and Q3 by 0.5 meters. This is the first. So next U final, that is UF is equal to when the charge has reached to this particular thing. That will be the 1 by 4 pi epsilon naught of So it is initial charge, it will be the Q1. So since this extra distance, whatever is the radius of the circle is 40 centimeters, means this extra distance has to be the 10 centimeters. So from A to D, it is Q1 and Q3 by zero point 0.4 only, plus, and the last one will be the Q2, and this will be the Q3 by zero point 0.1 centimeters. So change in potential energy he is asking. So delta U is equal to, so you can go for the U final minus U initial. So U final minus U initial, you just need to substitute these values over there in that relationship, in this U final and U initial, and we need to go for the solving case. So when we substitute, what are the terms that are going to be cancelled? So your first two terms, that is this term in the first U initial and final, these two values are going to be the same. So definitely those two terms will be cancelled, and the leftover term is 1 by 4 pi epsilon naught. This will be the Q2, Q3 by, it will be the zero point 0.1 minus, it will be the Q2, Q3 by zero point 0.5. So that means you should have definitely Q2 should be there. That means your answer should be C or D. So on solving this one, so zero point 0.5 minus, this is going to be the zero point 0.1, that is zero point 0.4 by denominator. So when you go for the solving, you should be getting one of the answer of it. Fine, sir. So or else if I solve this one, this will be getting it as an 1 by 4 pi epsilon naught of, this is 4 into Q2 Q3 by, this will be the uh, that is zero point 0.4 and 0.05, or when you solve this one, so 40 by 5, it should be the 8 conditions. So next one, identical charges minus q are placed at the corners of the cube of the side B. Then the electrostatic potential energy of plus q placed at the center of the cube. So if I consider the center of the cube, or this the cube one, whose side is going to be the B, he has mentioned all the corners, that is 8 corners, he has placed minus q. At every corner he has placed a negative charge, that is minus q, and at the center he has placed an plus q. So at every corner minus q, minus q, minus q. The distance or the diagonal is going to be the root 3b. So the distance from the every negative charge to the center is going to be, that is r value is going to be the root 3b by 2. So all of the potential energies are going to be the same thing. Every potential energy value is going to be the same here. So we need to find out the only one thing here. So obviously when I put down here, the 1 by u is equal to 8 values will be there. So 8 into 1 by 4 pi epsilon naught. Both the charges are going to be the same, that is q square by, distance is going to be the root 3b by 2. Fine. So this is going to be yours. So when this is going to be going to the numerator, it's 16 by 4. So it will be the 4q square by root 3 pi epsilon naught b. The only option which is consisting of the root 3 is going to be this one. So now next one, two metal pieces having the potential difference of the 800 volts are zero point 0.2 meters apart. Two metal pieces are there whose potential difference is, that is delta V value is equal to the 800 volts. Delta V is 800 volts he has given. Fine. So now we need to find out the virtual that distance of separation, that is r is equal to zero point 0.2 meters apart horizontally. A particle of mass also he has suspended in an equilibrium between the plates. If in an elementary charge, the charge on the particle. So that means there are the two plates which are there. The potential difference between these two plates are going to be something 800 he has given. So it is in the equilibrium, means mg should be acting in the downward direction, and here force because of the electrostatic, that is eq, should be in the upward sense. Under the equilibrium, you can go for an eq is equal to mg. So electric field and the potential, we know the relation between the E is equal to V by D with a negative sign, obviously. Or here we are going for the magnitude, no need of that one. So it is going to be the potential difference, that is delta V by distance of separation, that is R, if I take into charge Q, is equal to M into G. He has given every value here. We need he is just asking the charge, that is N into E is equal to mg into distance of separation by delta V, or number of charges is equal to mg into distance of separation by delta V into charge value, which is mass is 1.96 into 10 to the power of minus 15. G value is 9.8 into this value is going to be the distance of separation 0.2 meters, and divided by the potential difference is going to be 800 into, and the value of basic charge is 1.6 into 10 to the power of minus 19. So this is the situation, sir. So on solving this one, you should be getting how many charges or n values you should be getting here. Fine. So next one, sir. Coming to the capacitors conditions now. Two parallel plate capacitors are separated by a distance of the dielectric as shown in the figure, net capacitance. So the charge which is entering or which is leaving from here, let us consider this as a C1 and this as a C2. That means both the capacitors are in a series combination. So C1 is equal to K1 epsilon naught A by D by 2. K1 value is going to be the 1 and 2 goes, that is 2 epsilon naught A by D, and your C2, that is the second capacitance whose dielectric value is K2, K2 epsilon naught A by D by 2. So K2 value is going to be the 2, so it will be the 4 epsilon naught A by D. Substitute in the series combination C effective value. C effective is equal to C1 C2 by C1 plus C2. So substitute these values. So it will be the 8 epsilon naught A by, this will be the 6D, 4 plus 2, or it will be the 4 epsilon naught A by 3D. So this will be your thing. Next one. Identical dielectric slabs are inserted in two two identical capacitors A and B. So identical dielectric slabs. This is one dielectric slab and this is another one. So these are the two identical dielectric slabs which are being placed in this situation, sir, please. Mm, fine. So this is the one which is being placed. Now what he is doing, these capacitors are having these capacitors and a chargeable battery are connected as shown in the figure. Now the slab of the capacitor B is being pulled. So this one he is pulling it outside. Fine. So what will happen? So when he is going to be pulling this one, since he is removing the dielectric, the charge which is already stored in the capacitor B, that will be reduced. So since the charge is going to be reduced in the capacitor, that flows to the battery. So now since it's going to be flowing through the battery in this case, so positive charge is will be flowing from the that is A to B. Okay, during this particular process, whatever the charge is there, that extra charge has to be flowing from the positive charge will be starts moving from the A to B. So this should be the better option in this case, please. Next one, a parallel plate capacitor C, with plates of unit area, the separation is being D, is filled with a liquid of dielectric constant K is equal to 2. the level of the the level of the liquid in this one is d by 3 initially. Suppose the liquid level decreases at a constant rate v, the time constant as a function of the time. What do you mean by time constant? Time constant is equal to capacity into CR. So we need to find out the capacity of this one for the liquid which is filled up to the d by 3. So for that one, after the time t, so I'm writing this one after time t, the thickness of liquid will remain. So that means it will come down. Will remain d by 3 minus velocity into time. Okay, so now if I want to find out the new capacities, that is C dash is equal to epsilon naught. Area is going to be something like epsilon naught. Area is going to be the unit area. It is given here, unit area. So that is 1 epsilon naught A by A into by d minus of d by 3 minus Vt. So I'm using the formula. Which formula? After introducing a partially dielectric, C is equal to epsilon naught A by d minus T plus T by K. So first part I have written plus d by 3 minus Vt by 2. This is the one. Okay. So dielectric constant, he has given it as n 2. So now on solving this one, how much you should be getting here? There is an LCM d by 3 is there. 3 comes down. Here it will be the 6. So 6 goes to the numerator. It will be the 6 epsilon naught. And if I also multiply with the r directly, I can get the time constant 6 epsilon naught r by. Your denominator will be. So this is going to be the 6d minus d. It will be the 5d obviously. 5d plus 3 times of Vt. Minus of minus will become plus. So 3 times of the Vt it will be. So it should be your first option here. Now, so see how we go. We need to solve this particular things, please. A capacitance of the parallel plate capacitor with a air as medium is 6 microfarads. So C is equal to 6 microfarads air as a medium. That means epsilon naught A by D, it should be its formula. With the introduction of a dielectric medium, the capacitance becomes 30 micro, that means C dash is equal to 30 microfarad because of the dielectric, that is K into epsilon naught A by D. Now he is asking permittivity of that means he is asking epsilon is equal to how much? Epsilon is equal to epsilon naught into dielectric or epsilon R. So when you go for the division of these two things, this will be the 1 by 5 is equal to 1 by K. So that means your K value is going to be how much, sir? You can put down the K value is going to be 5 here. Fine. Now substitute in this one, epsilon is equal to epsilon naught value 8.85 into 10 to the power of minus 13. Okay, so into this one is going to be the 5. So when you multiply 25 to for 42 for this one, so 44, so something around 44, 3 to so 44.25 it will be. So 44.25 into 10 to the power of minus 13, or you just readjust it. So it should be the sum 0.44 into 10 to the power of something minus 10 like this. So here you can go for this one, please. Next one. So in this question, it's a pure case of a dielectric slab. So this is a graphical, pure graphical. So same type of the questions can also be asked with respect to the potential taking into consideration. So two thin dielectric slabs are there. One is K1, another one K2. He has clearly given that K1 is less than K2. So what will happen when we introduce a dielectric between the plates? Electric field reduces by K times, that is E by K, K1, and this will be the E by K2 here. So between the plates of the capacitor, the electric field at every instant will be the constant from P to Q. That is E is equal to sigma by epsilon naught. It will be always remains constant. Whenever there is a or the place where dielectric is introduced at that particular point, your electric field is going to be reduced by sigma by K1 epsilon naught here. Since K1 is going to be smaller value, and so here the E value should be higher. That means that at this location E1 should be higher than your E2. That is E2 is equal to sigma by K2 epsilon naught. So if you compare these two things, since K2 is 4, E2 should be less. So E1 has to be greater than the E2 conditions. So this is the E1 location here, and this is your E2 location here. Now observe the graph here, E1 has to be higher than the E2. So this is the location where the E1 might be there. This is the location where E2 might be there. So remaining at all other places, it remains as a constant. So the better option is going to be the option C. Fine. Next one, sir. Two parallel metal plates having the charges plus Q and minus Q each face each other at certain distance between them. If the plates are now dipped in the kerosene oil tank, the electric field between the plates is kerosene. For kerosene, dielectric constant will be greater than 1, sir. So since it is greater than 1, on introducing the dielectric, electric field will be decreased by K times. So, and K value, since K value is going to be greater than 1, so electric field will be decreased. So it can be the option C. Next one, sir. A parallel plate condenser with oil between the plates. So a parallel plate capacitor is there like this. He is filling the oil between the plates of the capacitor here. If oil is removed, then capacitance. So initially, there is a dielectric here with a K value. So that means initial C value, I'll consider it as an K into epsilon naught A by D. But your dielectric value is 2K or 2 epsilon naught A by D. Now, since the dielectric is removed, C dash will be only epsilon naught A by D. So if I want to compare this one, this will be become as an C by 2 if I take this 2 to the other side. So it is an option D case here. Now, a slab of copper of thickness B is inserted between the plates. It's partially inserted. So total is not included over there. Between the plates, partially filled. The separation between the plates is going to be this one. B is equal then the ratio of the capacities of the capacitors before and after inserting the slab. So before inserting the slab, capacity will be obviously epsilon naught A by D. And after this is before, and after inserting the slab, partially he is inserting, this should be epsilon naught A by D minus T plus T by K. This will be the relationship. But since he is introducing the copper, and copper is a metal, and for metals, dielectric constant K value is infinity. So this term will become 0. So after will be epsilon naught A by D minus what is the thickness he has been introducing B. B is nothing but a D by 2. So it should be the epsilon naught A by D by 2. So now he is asking after and before, that is C after by C before is equal to 2 epsilon naught A by D by epsilon naught A by D. So this ratio should be 2 is to 1. So like this, one of the condition please. Next one, sir. A parallel plate capacitor of area A is there. Okay, this is one of the typical model questions where the multiple dielectrics are being introduced here. So distance of separation is been there. So half of the distance of separation. In the sense, suppose the charge is coming from the plate A this side, and it is been moving in this direction like this. So now, how do we consider this one? Distance of separation is going to be the D, and initial capacitance is going to be the C, is filled with the four dielectric materials having the dielectric constants K1, K2, K3, and K4. K4 is completely taking the area, but K1 is half of this one area. This area is been dividing A by 3, A by 3, and A by 3. Distance is half. If a single dielectric material is to be used to have the capacity, same capacitance, he wants to have the same capacitance. This is a very important condition he is asking. Then the dielectric is going to be how much? So it should have been the same capacitance. I want that means K effective he is asking. So if you consider this portion as a single capacitor one, then the C1 value can be written as that is K1 into epsilon naught. Area will be A by 3. Distance of separation is D by 2, or it will be the 2K1 epsilon naught A by 3D. Okay, so this is the main important thing. So C1 we have got the value here, please. So now let's go for the another case that is called as in C2. So C2 is also the same thing, but only the dielectric value has been changed. So that is C2 called directly I'm writing here. That is 2K2 epsilon naught A by 3D, and C3 value is also same. That is C3 is also 2K3 epsilon naught A by 3D. So this is our relationship, sir, please. Now, if I write for the C4, so that is the fourth capacitor which is occupying the total area. So it will be the K4 into epsilon naught total area by distance is D by 2. It will be the 2 K4 epsilon naught A by D. Right, sir? So this is our relationship, please. So now, if all of them, how they are being connected, C1, C2, C3 are in parallel. So C1, comma C2, comma C3 are in parallel. These are the things which are in the parallel conditions. So they are parallel. So now see, and that the combination is going to be in series with, okay, this is in series with C4. So what is the parallel combination will be C1 plus C2 plus C3. I'm going for the total thing. So 1 by C effective can be written as an 1 by of this is C1 plus C2 plus C3, and that is in series with the C4. So how these three are in the parallel condition? How these three are in the parallel condition in the sense? So this is the situation. This is the one plate. If I consider, if I am removing or eliminating the four, and we are checking this one, this is the one portion. Second portion, this is your third portion. So charge is been same, and all of them are experiencing the same electric field and everything, so that all of them are going to be in the parallel combination. Or else if I draw this diagram like this, it might be comfortable for the visualizing. This is your first one, this is your second one, this is your third. So all of them are in the parallel conditions. Fine. So now coming to this one, on substituting C1, C2, C3 values, we can find the effective K value is going to be how much? Fine, sir. So you can just put down these C1, C2, C3 values, and you can just solve it. you will be getting your effective C values mostly. So next case, please. Three capacitors, each of capacitance C and of breakdown voltage V are joined in series. So three capacitors are there. So all of them are the C and the breakdown voltage is V are joined them in the series. So if three capacitors are joined in the series combination, this is C, this is C, this is C. Then effective C effective value will become as an C by 3. So if the effective capacitance becomes C by 3, then what is an voltage over there? Then total voltage or the breakdown voltage is going to be the stored charge by C effective or new value of this one, which is C by 3, which is that means nothing but a C into Q by C. But what is the Q by C is initial breakdown voltage, that is going to be the 3V. So it should be the C by 3 comma 3V. And in the next section, this one, the a network of four capacitors are being given. C1 value is going to be this is C. This one he has mentioned it as an 2C. This is 3C and this one is 4C. So all these three of them, that is C1 comma C2 comma C3 are in series. This is the given thing, please. So since all of them are in the series combination, then the effective will be C effective is going to be the 1 by C1 plus, that is 1 by C plus 1 by 2C plus 1 by 3C, that comes out to be the 6C by 11. That let me take it as an some C dash. He is asking the charge ratio between the C2 and C4 means C dash and C4 will have the same whatever he has asked, this one. So since the potential is going to be the same, so charge ratio of the, that is Q2 by Q4 will be equal to the directly proportional C dash by that is C4. Your C dash value is 6C by 11 and your C4 value is going to be the 4C. C goes off here 6 by 44, which comes out to be 3 by 11. So this should be, so 3 by 22. Yeah, sorry. 3 by 22, this should be your option, please. Next one, a capacitor of capacity C1 is charged up to a potential V volt and then connected in parallel to an uncharged capacity C2. So that means C1 capacity is first capacitor is C1 and the potential V1 is equal to V. Capacity C2 is C2 only will be taking and V2 is since it is uncharged, it will be the 0. And directly we can go for the common potential thing or you can equate the charges, that the charges are going to remain same Q1 plus Q2 before joining and after joining Q1 dash plus Q2 dash it will be same, or common potential can be written as an C1 V1 plus C2 V2 by this will be the C1 plus C2. C1 V1 can be written as an as it is C1 V1, but this one is going to be the 0 by C1 plus C2. So which can be our option C1 V by C1 plus C2. This is going to be our condition. Next one. What is the effective capacitance of this particular thing? So it's an Wheatstone bridge one. So it's a balanced Wheatstone bridge. So since it's a balanced Wheatstone bridge, this particular terms will not be, it's going to be ruled out here. So 6 and 6, these two are in series. So since these two are in series, the effective becomes as an 3, that is C1, C2 by C1 plus C2. C3 and C4, these two are also in series. Then the effective capacitance becomes your 3. It will become half C1, C2 by C1 and C2, C1 plus C2. So now these two are in parallel condition. This is X and this is Y. Since both of them are in the parallel condition, so C effective will be equal to the 3 plus 3, that comes out to be your 6 microfarad. So this should be the condition. It's a balanced Wheatstone bridge condition, sir. Next, two identical capacitors C1 and C2 of equal capacitance are connected as shown in the figure. The terminals A and B of the key are connected to the charged capacitor C1 using battery of the EMF volt V. Now disconnecting the A and B, the terminals B and C are being connected. Okay, so he's removing the battery. So before removing the battery, the energy stored in this one will be the U half C1 V square. This will be the energy stored initially. So now what he is asking, sir? C1 V square, both the capacitance are going to be equal capacitance he has given, so I'm taking it as an half CV square. Now, since he is disconnecting, what is the percentage loss? So, whatever the total energy initially there with the C1 equally distributed between these two things. Since both of them are going to be in the series combination, the charge will be same, or you can go for an loss of energy is equal to, you can go for the theoretically, or you can use the formula, that is loss of energy is equal to half C1 C2 by C1 plus C2 into this is V1 minus V2 whole square. Initially it is uncharged, so potential of this one is going to be 0. It will be the half C into C by 2C, as I have told you. It's going to become half equal capacitance, so it will be the V minus 0 whole square. So this will be the half or 1 by 4 CV square. So initially it was half CV square, now it is 1 by 4 CV square. That means loss percentage is 50% loss. So this should be our answer. Next one. Two condensers of capacity C and other of C by 2 are connected to a V volt battery as shown in the figure. The work done is in charging fully both the condensers is going to be how much? So since they are connected in the parallel conditions, the effective capacitance, or you can go for, or the total charge, whatever is there, will be distributed in this one as a Q1 and in this one as an Q2. So I can write the total charge distribution Q is equal to Q1 plus Q2. So charge can be replaced with the C into potential, since they are parallel, it will be the C by 2 into V. So total charge is 3CV by 2 here. So this is your total charge or the net charge in this. So work done is equal to, you can go for an half QV, which is equal to the half of 3CV by 2 into potential V, which is equal to the 3 by 4 CV square. So that will be your next option. Fine. So this completes actually the today's models of the questions that we have discussed regarding the electric potential, and as well as some questions regarding the electrical, that is capacitance. Hope you have understood these things. All the best to each and everyone for your NEET examinations.